working on a variety of things. I had really hoped that as he came as a visiting scientist, he would get one thing done, and he's worked on several projects, which has been pretty amazing for us. To give you context about Gerald, he comes to us from a background of computer science and software engineering, working specifically in the space of medical imaging. And I think the thing that I was most attracted to Gerald when we first met was the fact that he is very much a MacGyver, if you will, of medical imaging, and the fact that he leverages so many different technologies to accomplish his goals. And so he's worked in many of the core technologies that we're used to in medical image processing. He's developed many of the algorithms in different spaces. The work that he's going to talk about here is work on, as a lot of work is today, in deep learning, but it's an approach to deep learning that is fairly rigorous. It brings in a number of different concepts, including some of his prior research, to build a better strategy for segmenting medical image data. And it's been a huge positive experience for the lab. He's engaged with a number of people in the lab. So hopefully tonight we're going to hear about this technology, which will get you guys excited to kind of dig a little bit further in. Gerald.
Thank you, David. Yeah, so what I will focus on today is classic neural deep learning models, but focusing on the pre- and post-processing steps. So regular image processing, computer vision tasks introduced and combined with deep learning. Yeah, my biography, I've been all the time in the medical domain, doing all my diploma thesis and my PhD thesis in the medical informatics domain, mainly on functional segmentation of vessel structures and segmentation tasks in a general point of view. And since 2016, I'm senior researcher at the research group. Can we remove that? That image there somewhere? I don't know. Anybody knowing how to skip the...
You keep going, I'll try to get it.
Okay, I keep on going. So since 2016, I'm very much involved in a research group in Austria for advanced information systems and technology. So we are tackling all the sensor devices, different aspects of software engineering with a strong focus on the medical domain. So our members from the research group are in the DICOM committee of Austria with all the standards and all the medical communication staffs involved. And since July, I had the pleasure of being here in Rochester at the Mayo Clinic at the PRI and doing all the research stuff I'd like to do and had no time to do in the past. Yeah, so brief content of my talk today. First, give a motivation why liver image segmentation, all the domains where it is applicable. Give just a brief glance on the state of the art. I'm sure you all know the key concepts, the classic image processing strategies, as well as the novel deep learning concepts. Then, around the first half of my talk, we'll focus on the UNet segmentation with some pre- and post-processing steps. And then, second half of the talk, I will have a look if it is possible with GraphCut, if the black box nature of deep learning models, you can keep the results or skip them, but there is no way of adapting them. So to make deep learning models more user interactive, we have had a look at GraphCuts and how to adapt them for high quality interactive post-processing. Then I will also talk about another domain, while my first part of the talk is liver data from CT. We transfer it to MRI, where we have only a few datasets, so much less data available for retraining all the stuff. And finally, I will discuss and present some evaluations on GANs for synthesizing medical data exactly in these domains where you lack data for training your deep learning models at a very, very high accuracy. Yeah, motivation, we all know why we're doing segmentation. It's surgery planning, surgical training, everywhere where you want some quantitative results on the volume, follow-up studies, how large was the tumor prior and post the intervention and the therapy. All that only is possible with a precise segmentation available. And another interesting aspect I've done many research work in is functional classification. So if you have your segmentation of organs like the liver and of the vessel structures with hemodynamic analysis, graph analysis, you can do some functional classification like liver lobe classification based on the vessel systems. Yeah, and of course, 3D print is also an emerging technology where you need your high accuracy segmentations at the first step. Yeah, state-of-the-art in image processing, I start with all the stuff done some decades ago. Region growing live wire, if you have an expert willing to put in some level of user intention, it's pretty good tool for, let's call it segmenting around 80% of all anatomies around there. Other methods like deformable models or statistical shape models or active appearance models have a higher level of automation, but it's pretty much effort to adapt them and adjust them to the specific medical segmentation domain. Yeah, level sets is also a mathematical concept that allows for pretty automated segmentation with only few input parameters to specify by the user. In the same direction, watershed transform is a pretty good tool for pre-segmentation of a data set if you want to define the segmentation task itself as a feature-based classification approach. So you get your small regions, homogeneous regions, preferably all belonging to the same anatomical regions. Yeah, so we have region growing, live wire, if you're willing to input some effort, statistical shape models as we have trained for the left ventricle shapes. A work of mine in the past, some 10 years ago, SliceWise processing of CT data of the liver with fast marching level sets for the initial seeds and then threshold level sets for propagation in a bottom-up and top-down approach running fully automated. Also a 3D segmentation domain like the liver segmentation processed in a strictly slice-wise optimization approach. Well, here we see classic deformable models. Yeah, so now in the machine learning domain, much work is going on. The classic feed-forward networks with only only a few hidden layers. They are getting larger. All the hidden stuff in between is getting deeper, and with some around 5 hidden layers, I would already call them belonging to the deep learning domain. Other interesting stuff there was the coherent self-organizing neural networks, where you can do any classification, clustering of complex input data. Of course, the data layout itself is a strictly grid, but on a virtual level, the grid gets clustered, deformed, like we know for elastic registration in the computer vision domain. Other very important things are recurrent neural networks. specifically the long short-time memories. With these, you can incorporate some knowledge of the previously seen data of the sequence of the images you process. That is very relevant in the semantic interpretation as for speech synthesis, speech recognition, everything, also natural language processing, where letters or words are not occurring in a very random order, but are an output of some underlying semantic, of some underlying grammar. And that is involved there and incorporating. So if you have some grammar, some rules of your input data, this is a very interesting strategy to model and address these topics. The most important aspect and also the bridge to the classic image processing are the convolutional neural networks, where the convolution is the most important operation as it was, from my point of view, also in the image processing domain the last 40 years. You can go there in two directions with pretty the same network type, doing classification, like here for an input image, is it a beach or a city? Or if you have the full encoder, decoder pattern, you can also output an image classified, fully segmented, with multiple labels at the same higher or lower resolution as your input data was. And that is a clear benefit over classic computer vision aspects like Haar cascades or some pyramid multi-resolution approaches. Yeah, that was the state of the art. What have I done in my PhD thesis? This was shortly prior to this deep learning boost. On the one hand, very unlucky. So I only had recently the chance to look at deep learning. So what I tried in my thesis was to develop a fully automated feature-based segmentation approach where you train your models on only a very small amount of tomographic datasets. So domains like brain MRI or CT of the abdomen only with some 10, 15, 20 input datasets that are that ship with a high quality reference segmentation. So what I've done there is some pre-filtering, then edge detection based on the edges, watershed, pre-segmentation with some improvements that you don't run into problems where the edges are weak. So I've stabilized it in a hybrid approach. And then you have this fancy pre-segmentation where you have some 1,000 regions per slice, not knowing to which anatomical structures they belong. But with the premise that every of these small regions is fully located within a target anatomy, not on the borders, not connecting two regions. This kind of pre-segmentation is pretty good, usable for some classification approach. So the segmentation itself was then a feature-based segmentation where the features are automatically segmented for the specific domain. So the algorithm selects these features that work best for MRI datasets of the brain or CT datasets of the abdomen or whatever the domain is. I worked with local features and with meta features that evaluate the interclass statistics. So if you do that with some input, like here for the brain map data sets, you get pretty good, fully automated results. So back to my talk today. Our material, our data sets come from the medical segmentation decathlon. There are 131 volumes, which is pretty a large number and sufficient for the most deep learning models to train. In the dataset reference segmentations, there are 3 classes. The background, the liver, and the liver tumor. As we only address the binary segmentation problem, we combine the liver and the liver tumor. So to get the full shape of the liver, despite if there is some cancer involved or not. Yeah, the data is from different vendors, different hospitals, different medical experts providing the reference segmentations, different tools that have been used to provide the reference segmentations, but this heterogeneity is not a bad thing for a machine learning approach. So variability in your data helps a lot. I think that is also a strong benefit of the dataset itself, not that you all have a free amount of sufficient data, but also that it has some variability involved. Yeah, of course, there are also some drawbacks. Some did segment the vessels, others did exclude them from the final results, but these are all things a machine learning approach should be able to handle during the training process. Yeah, so what we have overall is some 27,000 slices after adapting the spacing. So we are using ISO voxel spacing, doing some interpolation to get it. From the 27,000 slices, we use 22,000 for training and the remaining around 7,000 for validation and test. I only had to correct one dataset, the volume 102, because I was a bit suspicious about the liver region below there. So that part was removed. The volume itself wouldn't make any difference, but if you have a segmentation approach that incorporates the region of interest as a starting position, this would totally disrupt this test dataset. Yeah, so the pre-processing is some kind of windowing intensity profile adaptation. The intensities are scaled so that the mean liver intensity is located around 127. We use 8-bit unsigned. With this scaling, we restrict the datasets to the region of interest. For the given input data, this is straightforward done with the provided reference segmentation. And also, if you have the reference segmentation, you can do all this statistics and linear intensity transformation. But also with real-world testing is no big deal, because restricting your data to some region of interest and doing your classic windowing is not a big deal, and that is the only required input data for our then fully automated segmentation approach. Yeah, so there are some transformations. We use Lenkos interpolation for the slides, and Lenkos and cubic, and for the shape itself, for the binary reference segmentation, we use some shape interpolation to get really and conserve the binary shape of the regions and not get some decreasing values of the binary mask. Yeah, now let's talk about a very important topic for training deep learning models. It's data augmentation. Of course, it would be best if you had an infinite amount of reference segmentation you could train on. That is not realistic in practice. But also if you had, let's say, 100,000, 200,000 or millions of input slices, it would still be a wise decision to apply data augmentation, to get some bias into the data to some artificial bias into the data. What we use there is translation as geometric transformation, also rotation within some random range, besides adaptations on the intensity profile itself. So in a multiplicative and in an additive way. That is how we manipulate the input slices when we use them for random data augmentation in the model training. So we have there some static parameter set that defines the limits of the random data augmentation. And with that, it's another wise decision to incorporate some additional boundary here marked in red, not to have the risk that your target structure is getting out of the visible area due to the randomness of this data augmentation. Yeah, and another aspect is that all of our slices are transformed to 372 times 308, including this boundary of 10 pixels around. Where does this size result from? It's a mean aspect ratio of the liver in these data sets calculated for all 131. Most of the networks just use squared dimensions, squared size, but it's absolutely no problem. Of course, the numbers have some trick with respect to the unit, so you have to get the possibility to divide the size there at the 5 resolution layers. So they are rounded to the best appropriate extension fulfilling the unit multi-resolution pyramid restrictions. And another thing, I will later on talk about some multiple slice approaches, incorporating the previous and the post slice. There also data augmentation is used, but not in a fully random way. So if you have a small mini batch of slices, it would not be wise to rotate them randomly around, but there the data augmentation range is restricted to a quarter to have a better correlation of these subsequent slices. So what we use for training is an UNet, a 2D unit adapted from Ronneberg. We use padding so the size is not further restricted with the lowering pyramid levels. All working with cross entropy as loss and atom optimizer. And there we see the adapted unit, also with 5 levels of hierarchy, and with some feature maps evaluated on each hierarchy level. Yeah, so the unit comes with the encoder-decoder pattern. First, the slice size is reduced, and then scaled up to the original output size, feeding in the original results at these previous steps to concatenate all together when rescaling to the larger original resolution. That is what we train. Yeah. So doing 2-dimensional UNet processing for a 3D-dimensional task where others train 3D units will maybe not be the end of the range one can achieve. So from the very first beginning, we also had in mind how can you improve slice-wise processing that you can approximately reach results as they are achieved by 3D approaches at the state of the art. So our idea there was to incorporate orthogonal views, coronal, sagittal, besides the axial processing, and then to combine these three results from axial, coronal, sagittal view all together, also with training another unit or just doing some averaging. And another idea we had in mind was training specific models for specific sections of the entire volume. Yeah. So here with the specific models, in this case 5 models for the entire volume, if you evaluate the mean size in pixels of the liver diameter from the very top to the bottom, for the first 5 datasets, they all follow quite the same statistical behavior, increase in size, decrease in size. So if you incorporate that and split your volume, you have very characteristic cross-sections at the cranial area, in the mid-section, and in the caudal sections. So if you train an individual model for these 5 sections with some incorporating of both models for the border areas, one would expect better results compared to only training one axial model. Yeah, here we see once again the problematic sections. At the very top in the area of the heart, you have very, very few pixels as input if only the axial view is incorporated, so the model has hardly any information what to segment there. The same is true for the bottom area. So in these sections, it's pretty hard for the axial model to process the 3D volumes in a fully slice-wise way, not incorporating previous information as for the long short-time memory approaches. Yeah, another aspect important is the incorporation of sagittal coronal. So from any volume you can directly transform your orthogonal views and train additional 2 units for these views. So what you get are 3 binary results, and if you transform them back to the axial view, you have 3 almost the same but slightly varying outcomes of axial sections. The ones that are really axial and the others that have intermediately been processed in another direction. And combining these 3, we also expected some improvement of the axial slices. So how to combine them? I had a statistical shape model in mind with the premise that in the cranial caudal area, the axial model is expected to be worst. So if you consider a cube, axial, coronal, sagittal is strong in 4 of the directions of the cube and weak in 2 of them. And by averaging or combining them with a unit, or in this case with a statistical shape model, the majority of the 3 votes should be right in a hopefully majority of all cases. So the first approach there was some statistical shape model exactly for this combination. And we also have evaluated simple averaging of the 3 outcomes and training another unit for doing this task of combination from axial, sagittal, coronal after back transformation. Yeah, and the last idea we had in mind, how to incorporate a mini-batch. If we have some prediction for the previous and the subsequent slice, does this help improving the accuracy of the current axial slice with the information previous and post the slice, and to apply it in a bottom-up, top-down way of post-processing your initially axial segmentation results. Going through all the data once again and combination of the currently intensity profile with the prediction of the previous and the subsequent slice. So these are the three improvement strategy we have had a look at. So starting with a simple Excel model, it got quite complicated, as you see on the chart. So combining all of these optimization approaches, we are far away from one SliceWise unit. We rather have some 7 units trained for processing of the tomographic volumes, putting all these optimization approaches together. So how are the results evaluated? Simple metrics, dice coefficient, the more restrictive Jaccard index, and then interesting metric, the normalized surface distance, which does not only take into account the false positive, false negative voxels, but also how far away are they from the next inside or outside pixel respectively. So how far away from the two true segmentation masks are the false results? While for the dice and the Jaccard index, that isn't taken into account at all. Yeah, so what do we get with the Excel model and also the sagittal and coronal ones? It's good dice coefficient of 96%. And Jaccard index 92.6. So maybe for a clinical practice this is not sufficient, but for a first start it's not that bad. Here you see the false positive and false negatives of one volume. It's volume 101 with the missing parts in red and the surplus parts in blue. What is missing in this rather caudal slice? The mid of the liver section, totally missing, and here on this slice also some parts missing. Exactly what our hypothesis was. In the lower and upper slices, the Excel model alone might not perform very well. So incorporating coronal, sagittal, if you have a look at where are they of highest accuracy, you see in the lower sections the sagittal, coronal are pretty good, better than the axial. At the top, close to the heart, it's not what we expected, exactly the opposite there. The axial model is still good, better than the other. So our premise is the results are different from the orthogonal views. You see it here in the midsection. There is the axial output missing, but the midsection is classified from the other two orthogonal views. So as long as for every voxel 2 of the 3 models are right, you have all the possibilities to get a very, very accurate segmentation after all. Yeah, training process, for each of the units, it takes around 15 to 30 hours. Evaluation is then performed on millisecond basis for every slice, and due to the aggressive parameterization in some 50% of all training processes, you have some stagnation. Like you see here in the chart, where there is no progress at all, either at 80% or 60% or 40 or 20%. I don't know why this ships in distances of 20%, where you get stuck and there is no progress at all. But if you get above 80%, it trains until the end, pretty solidly. Also, due to the data augmentation, both the training and the test accuracy are increasing. I haven't used too many datasets for validation, so there is quite some fluctuation in there. Yeah, so what is it with the 5 models for the sections, top section, mid sections, and the lower sections? We had the expectation that we could improve the results there. You only have to look at a very small area where the cross sections are very similar in shape. So what the UNet trains is, on the one hand, intensity profile, shape, and location. And of these three aspects, you could help the UNet with taking out the specific shape and location of the area for a regular human liver as it increases and decreases. But what we saw there was that the entire axial model in the specific section, in the lower section, it is worse compared to the other section, did slightly perform better compared to the models that are only trained on a on 20% of the entire volume. That was not exactly what we expected, and the reason is pretty obvious. UNet is pretty good in handling all the data. It can achieve multiple class results, and also it can handle changes in location and shape. So what is the problem there? Why is the section-based model performing weaker compared to the overall model? Any guess? It only has to look at a small section of the entire volume, and the liver cross-sections are very specific to the region. So the idea is not bad at all. It should outperform, but it doesn't. What's the problem in there?
Training set small.
Yeah, that is there. Reducing your training set to only 20% is much worse than having a very diverse set of input slices. If you exclude that bias, if you reduce the training set for the overall model too, it totally outperforms the small data set. So with a fair chance to get the same amount of input slices, these section models lead to improvement. So if you have enough data sets, if the amount of data sets is no problem, it's still a good idea to improve classification models, but only if you exclude the bias of your data set reduced to 20% size. Yeah, you could say an Excel model trained at 100% performs quite the same as the section one with only 20% of the data sets. So that was the reason why we skipped these section-based models from there on. With the previous and subsequent slices involved, so the current intensity profile enriched with the classification guess previously and subsequently, one gets significantly increased results. So 96 goes up to 97. For axial, the same is true for sagittal, coronal. So this increase in 0.4% might not look like an evolution, but it's pretty much also compared that you will not get deep into the 90s, as you always have the bias of inaccuracies of the reference dataset itself. So it's not 100% clear what is the segmentation of the liver itself. As it is subjective to the medical expert, you have some bias, some inaccuracies therein. So also comparing with your ground truth will always lead to some error. So I would say these 0.4% are really a large step you can take for all of the directions. Not only axial, but also sagittal and coronal. And one test performed too, axial with true, original, and the prediction of the subsequent one. So what is if we had a ground truth at one side of our Minibitch, then the results are really getting better. That is maybe what I would consider the somewhere close to the optimum where you can get if you stabilize the results. Why is that test run of relevance? Of course, in practice, you have no ground truth, but that shows the potential for one more bottom-up, top-down improvement run. If you use some interactive tool as GraphCut, as I will have some minutes to talk about later on, if you take time to improve some of the incorrect slices and rerun it, these improved results will boost it once again. So these mini batches, 3 slice mini batches, did really improve the results. Axial going up, sagittal going up, coronal going up. Here, 2 things are compared. If we use the model for the mini patches trained only on the axial, also for the coronal and sagittal, or to train them in a specific way, so that our sagittal coronal view also has this specifically trained mini patch in. Results are pretty the same, so one could argue if the axial one perfectly works and boosts the data also in the other orthogonal views, why would anyone incorporate there a specifically trained model and another model that makes all the UNet cascade more difficult and more complex? It has one significant advantage. Using the axial one, you already have the axial information included together with this sagittal coronal one. To keep that bias out, results were better when the UNet for the mini patch was trained for all views in a separate way. Yeah, so combining them, unluckily the complex statistical shape model exactly led to the same, at least good results as the average model. So there is no need to do complex statistical shape models, at least not in the way I did, as the 2 out of 3 votes really works good. So if you have these improved axial coronal sagittal views, and if you combine them in an averaging way, you really can boost your results. 2 out of 3 majority voting here really works as well as the statistical shape models. Having a look at the digit behind the comma, the statistical shape model would be slightly better, but not relevant at all. And training for that task of combining 3 slices into one can use once again a separately trained UNet, which is here indicated as model. Then results get slightly better once again, compared to the 2 out of 3 average voting. Yeah, and here with the prime, A prime, C prime, S prime, that is the one where also the mini-batch previous post-slice optimization was included. So playing out all the tricks, all the aces, this is what we can achieve with our UNet cascade, doing all the optimization strategies. Yeah, so the results, the slide I have shown you previously with incorporating of the orthogonal views is not a big deal at all. You get solid, stable results all, in all directions of your volume. Let me show you some quick videos. Once again, with red and blue, the minor position where there are some inaccuracy, either from the reference segmentation itself or from our classification approach. And another data set to quick view. Yeah. It's always in the vessel area where the vena porta launches in, where it's pretty unclear what should belong to the liver or not. Not only for the medical experts, but also for the UNet itself. Yeah, so comparing the results, what we have achieved in our work, comparing them to my level set SliceWise propagation I've done some 10 years ago. It's some 4% above, with pretty the same strategy, but a pretty much stronger technology with the deep learning models, and comparing it to the medical decathlon, yeah, the results are even a bit better to the result outcome there, but with one significant drawback. We have reduced the classification problem from 3 classes with the tumor to 2 classes, and of course for the medical decathlon, not even the restriction to the region of interest or the intensity profile or any user interaction is allowed, and also the medical decathlon data, as it is a decathlon, works for several diagnostic domains. So it's not a big deal to outperform them with one approach that only tackles one specific domain. So what we also have a look at, how easily can all the stuff be adapted to different domains. Yeah, there once again, there is some user interaction required, but only user interaction you perform anyway as a medical expert when you have a look at the data. Everybody is doing some windowing. Everybody can restrict the volume to some bounding box for the region of interest. Or one could automate these process steps too, if required. Yeah, so let's have a look at the application to other domains. We had a look at some liver datasets where we only have some very few datasets. With reference segmentations, there we use 13 for training, 2 for test, 1 each with HCC. And if you apply the CT unit model, you get horrible results, as shown there. Chacon index of 60% is not any good. So if you get that segmentation outcome where there are large parts missing, that is not a thing you can use in clinical practice. It's interesting there that this region where there is a discrepancy in intensity is perfectly handled by the CT models. Also this very vessel area and the very easy section there is totally missing. Why is that? With our approach of the pre-processing, windowing applied, scale applied, we at least had the hope that that would make the approach generic. From the target structure point of view, it is generic. But what is the problem there for the unit? It's not the liver itself. Either CT or MRI, also if the texture is looking different, that would not be a problem. But the real problem is not addressed by the windowing function. It's the background. The background is totally different in CT and MRI. Just have a look at bones. On the one hand, they are white, high intensities. On the other hand, they are black, as you only see the fat area around the bones. And that is the problem why the approach is not fully generic. Okay, so let's retrain the stuff. And yeah, you get some solid results. Of course, not the same as for the CT data, just because of the lack of data. With only 13 data sets compared to 100, you cannot train that well, but still for some slices, results are pretty solid. With all the same stuff as presented for the CT data, just rerun on the 13 MRI datasets. Yeah, once again with coronal, sagittal included, the 3 slice Minibitch, all the tricks. Some parts are missing or surplus, but anyway, it's not bad applying it. So what can we do with these suboptimal results? For clinical practice, it's not good if we have some error-prone regions. And that is now the interesting part. How can we get these deep learning models more interactive? The medical expert exactly knows if a region should be included or excluded. Yeah, and that brings us to GraphCats as post-processing tool for deep learning models. If you can train your user interaction combined with the deep learning models itself, a very fascinating work done here at the Mayo Clinic of Sakhalis. I think it's the Ericsson group, am I right? They trained a deep learning model together with some markers that can be moved by the medical expert later on. So the deep learning model not only learns how to preferably fully automatic process all the data, but also to react on 0 to n markers placed inside the dataset and then steered by the user. So to stay away from the background markers with the region, the foreground region, and so on. So if you can train all the interaction together with the model, this is a pretty fascinating stuff and helping a lot. But the only drawback there is that you have to rerun all the training once again with your interaction. So you cannot use a ready-to-go trained model. You have to rerun all the training together with the markers. With graph cuts, that is not required. You can use any kind of segmentation. A segmentation of statistical shape models, region coloring, whatever you want to improve, also and especially deep learning models. Graph cut, of course, is a much weaker segmentation approach. It has some relevance in video processing of RGB data, where it is pretty straightforward to extract your desired object. But to be honest, you cannot reach the same accuracy as with well-trained and unbiased deep learning models. So what we had to do there is to improve the classic graph cuts, so that on the one hand the user has the option to improve the results, and on the other hand we keep and conserve the high accuracy of our NewNet deep learning cascade. That were the two tasks we had to achieve there. And what our goal is, marginal trade-off in quality compared to the initial segmentation. Also, it's adapted by the user, and also in this graph cut, which is not that accurate, the trade-off should be neglectable. And the user interaction should be kept to a minimum. So nobody wants to do all the manual painting once again. The key point is there how to get the graph cut fitness function. It's not a Gaussian mixture model. We have to incorporate the original image, edges of the original image, expectation edges of the original image after some applied smoothing, and then 1 and 4 hits of our binary segmentation. Why do we have 4 segmentation results? The combined one, the axial, coronal, sagittal one. There it once again helps that all orthogonal views might lead to slightly varying results. Yeah, and the fitness function should combine all these 4 input images. These are the 4 inputs. Why do we not incorporate the 2 and 3 hit case, only the 1 and 4 of the 4 segmentations? They have no influence. These would only be the information along the edges, because it's the 1 hit is the wrong one in one orthogonal view, and the 3 or 4 hit is the average correct one. So 2 and 3 are not of that high relevance and would only incorporate bias. How do we get the weights? Not in an empiric way, but with evolution strategy, optimizing it for evolution strategy. Unluckily, you cannot optimize the weights with deep learning itself. That was my first try. And there you should think about the problem before you implement it, because the problem definition of graph cuts itself, as we have it, is you cannot differentiate. So from a mathematical point of view, you cannot optimize it. You cannot trace back which regions of the model to improve in a gradient-based way. So from the mathematical point of view, it cannot be trained with deep learning, so we had to use the evolution strategy. Yeah, we get these weights. Most important is the deep learning classification, but also the input image intensities edges are used. This is the fitness function. Most relevant with this maximum function combined are the original results, but also the intensity images are included. Yeah, and so what is the trade-off? The fully automated unit cascade, as we saw before, the card index is 94.3. And if we get the skeleton and the graph cut fully automated running, of course we have some drawback. Only using N4 adjacency in the graph cut and all the stuff where it performs weak, but the drawback is marginal. This is something I can invest in if, as a user, I have for the slices where there are some problems, the option and possibility to improve the results then. And what is if the skeleton for the foreground and background markers is derived from the ground truth, then the unit cascade is even outperformed by another %. If we had the right structures marked. So this 1% is inaccuracy that not the right structures are segmented. Not in an inaccurate way, but vessel left out or included, or some parts missing. So this is pretty promising that graph cut helps working out. So there we see the foreground background skeleton, fully automatic, derived from the deep learning outcome. That is the segmentation we get, and they are of comparable quality for the unit cascade. It's no interest to compare them. They are of same quality, but with the option to adapt in case of errors. Yeah, the skeletons are automatically derived with some border area as a morphological skeleton inside the region. I think we are a bit short in time. Do you want to see 1 minute of live demo, and then I dare to show you 10 minutes more of the generative adversarial networks, as they lead to very impressive results if you are short on data. With or without the live demo, you decide. It's not a big deal. I just show you for the first slide. So if we have there, either I can draw into the tool or get my seeds from the deep learning model segmented, and if there are no concave convex regions, it's pretty straightforward. Let's see another slice. Maybe do it in a user way. Nobody would do it when the deep learning model works well anyway, but let's just have a look. If you want clean edges, you need to grab into the edges, segment there, and you get pretty robust results. If you care about the 5 pixels left out above there, just put more marker position there. But for 95% of all slices, the deep learning model is fine. And for the ones where it is wrong, you now have a tool to adapt. Let's have a look at one more slice. Let's say we want this minimal gap there included here with the background seed. Sorry, that will not work out. Okay, if I want that gap, I draw into it, segment once again. Okay, that was. I should stay on the vessel area. Sorry. If you stay there, segment, you can also grab into these areas. Okay. Just to show you, the option is given to correct in case of errors. We also have done a small study. What is the effect of the foreground and background seeds as I have drawn them just before. If you don't hit the borders, you get pretty good results, and also the same results despite the foreground and background seeds. So we have three very different interpretations of graph cut intervention, but the outcome is always the same, and you have the option to add there this minimal top missing part with all three cases. Why is it that robust? Because it only takes into account the edges of the input and not the foreground, background, painting accuracy of the user. So when there is some error with graph cut, you correct it. Missing part, completed part, so with improving two datasets of the third thing, that was wrong, with putting two additional datasets to the third thing that have been automatically processed with the unit cascade. Results are bad, somewhere only close to the 90s. Apply the graph cut post-processing, retrain the stuff, it goes up. So only with two additional datasets that are post-processed in a semi-automated way, the results get up a bit. So starting in a new medical domain with only a few datasets, you can improve incrementally. First train your unit cascade, get some weak results, improve them with graph cut, retrain, and so on, and to improve the automatic quality in an iterative way. Another interesting thing is GANs. You maybe all know them. Two convolutional neural network types. One is discriminator with only one task to decide if two images are real or fake, and one generator getting random input and best approximating the outcome of the particular domain. So for celebrities, you can put that multi-pyramid GAN together and training on 200,000 celebrities with a very, very strong hardware GPU rack to train on. You get from these inputs these synthesized celebrities. They don't look similar to any of the celebrities, but similar to the characteristics of the celebrities. To have two eyes, a nose, a mouth, different hairstyle or whatever. Here we have two bold ones. At the beginning of each pyramid, you get pretty weak results if scaling up, but with some 200,000 iterations, results get better then for this kind of synthesized data. So what we have had a look at there was how to use it for medical data. If we are short on medical data, we want to synthesize a random amount of artificial data. Of course, if you do it with slices, like for the CT with Excel slices, you get out some generated slices. But the most important part for the data is that you get them together with a ground truth reference segmentation. And that is easy, achievable. While we had there an RGB tensor, we adapt the RGB tensor to a two-channel tensor, namely the intensity profile and the binary reference segmentation. If you do that for your training set, you get also a two-channel output. Your perfect matching ground truth for your synthesized input data. That is maybe the most important part. You get an arbitrary amount of reference data. If you don't need your input slices, you at least get a really large number of reference segmentations for these domains. Yeah. So what is it about? Unluckily, we have used a very, very large amount of datasets for training. So not a good argument for discussing that for a domain where you are short on data. So right now I'm retraining all the stuff with only 5,000 input datasets, and results look absolutely the same as I've turned on the data augmentation for the GAN training too. So the amount of datasets is not a big deal, but right now for the following results it was. Unluckily, I had very, very a large amount of input data sets. And once again, if you train something that runs for 2 weeks, you should think first, if the results are good, make them right and correct from the very first beginning. Yeah, so what we get at 4 times 4 pixel, you can see and identify them as medical data sets. If you scale up, they look pretty solid, pretty realistic. These are the synthesized data sets. The spine is at the right position. The ribs are there to be noticed. Everything is working out. At the higher levels, the 200,000 iterations were a bit short. So for the current run, I have increased the run in the upper sections so that this texture will improve. As we will see, a human can discriminate real data from this synthesized data, but the deep learning model is very happy getting additional data sets if they look like that, if the intensity profile is correct, if the shape is correct, if the position is correct. The deep learning model with all the convolutions and multi-hierarchies does not incorporate these texture issues at all. They are only relevant at the very highest pyramid level, because on the lower ones, due to the convolution, these will fade out anyway. Yeah, so let's test with some enriched datasets with some 4,400 real and synthetic ones. Where can we get? So testing a 4,000 real dataset on real-world data gives this accuracy. Reducing the data to 2,200, lower accuracy of the trained model for all testing datasets, real, fake, and hybrid. Interesting is a model only trained on the fake dataset is still somewhere 86 for the real-world data, which is not a big deal. I wouldn't cheer about 86%, but that is fully trained only on fake synthesized data. And as I have discussed before, if GraphCut is able to improve from 85–90%, this already would be a starting point only training on synthesized data. Nobody would do, because if you can train your gun, you have real data, and real data will always outperform. That is the interesting class, the hybrid model with 2,000 real, 2,000 synthesized. It outperforms at least the real world dataset. So things get better if you add synthesized data, and if you add much more synthesized data, you get close to the real world dataset. So if one says augmented datasets are 10 augmented datasets are worth one real world dataset, I would say 3 synthesized datasets are worth 1 real world dataset. Yeah, you can boost it. And there is another model train if you add some 5 inaccurate live wire segmentations. Then also you get a boost with the additional dataset. This variation on the segmentation tool and on the expert doing the segmentation has no influence on the quality outcome. I am at the very end, so what we see here, minimal real-world outcome and the one enriched by the GraphCut add-on to datasets. Nonsense what I'm talking, I should read. And the one of the synthesized model train. So training on 2,000 real datasets has some issues. And with the 6,600 synthesized one added for the model training, most of these inaccuracies are gone then. Yeah, that is only a glance to the future. As I'm already much over my time contingent, I just want to finally thank my research group in Austria, my members from the research group IEEE, very young students, most of them prior to their PhD, and our very experienced senior group at the Bayer Thanks for valuable discussion and input and helping out in discussing all of these partly crazy approaches. Thanks.
I know we've run long. Does anyone have any questions they want to ask? Okay, fair enough. Well, we'll thank our speaker one more time. Thank you all for coming. If you have any questions, you can always email Gerald. Thanks.